Okay, now the chemical reactions of alcohols and phenols. There are two basic type of reactions of alcohols and phenols. Okay, nucleophile, they can act as nucleophile and they can act as electrophile. It just depends on which bond gets broken. Okay, so if OH bond is broken, means hydrogen goes away. Then it acts as nucleophile. Alcohol or phenol, these act as nucleophile. But if CO bond breaks, for example, alcohol, you have C2H5OH, okay? Or write it like CH3CH2OH. If this OH bond is broken, then it acts as nucleophile because this is common sense. It means this part will act as nucleophile. Although remember that first, I will show you the mechanism. First, hydrogen will not get detached. That is the last step actually. Hydrogen gets detached. Hydrogen gets detached in last step. But you can see that if you separate hydrogen, this is actually the oxygen which will be deciding which type of reaction it will be. So it acts as nucleophile. But suppose if CH3CH2OH, CO bond, this CO bond gets this bond. In this case, if you see this carbon will acquire positive charge, it means it is looking for electrons. So this carbon will decide, although the reaction is not like this, I'm telling you, OH will get detached in the last step in the mechanism. But if you separate these two, OH and this part, OH is negative, this part will become positive. So this carbon will act as positive. It means it is looking for electron. It is acting as electrophile because it is looking for electrons. So I'm explaining again. If it is COH, this bond gets broken, this oxygen acts as nucleophile. If this bond gets broken, this carbon acts as electrophile. So alcohols as nucleophile, OH bond is broken. This is the mechanism, how it works. Common mechanism. You will get alcohol reacted with some carbocation. Okay, so if this is acting as nucleophile, it means there should be some positive part to which it should attack, on which it should attack. And remember the arrows. Arrows are always from negative to positive, opposite of dipole moment. So this oxygen will attack on the carbon and will get attached. First is addition. Remember the reaction is not addition reaction. Reaction is replacement reaction. Okay, substitution reaction. But first this intermediate, addition intermediate, because this pair of electron attacks on the positively charged carbon and gets attached. Now this carbon cannot have 5 bonds. Okay. So what happens actually, or this oxygen cannot have, this carbon has 4, right? This oxygen cannot have more valency than 8. So that's why this hydrogen gets detached. This hydrogen gets detached and any product like this will be formed. We will see the examples when alcohols act as nucleophile, but mechanism you need to memorize. This mechanism appears quite a few times, that when this alcohol reacts with this one and with what one, I will talk about that. The mechanism will be similar. the whole alcohol will get attached to the positive carbon. Remember, this whole alcohol first got attached. This whole alcohol got attached. Then this hydrogen got detached because oxygen cannot have valency, okay, or electron more than 8. Alcohol as electrophiles. In this, CO bond is broken and mechanism is now H plus first gets attached. So first is protonation. This step is called protonation. When this hydrogen gets attached on this oxygen, why it gets attached on this oxygen? Because this oxygen has pair, lone pair. After that, a nucleophile. Remember, the alcohol itself is acting as electrophile. Okay? So that's why it is looking for, this is acting as electrophile. The other species will act, might act as nucleophile. So how this happens? This happens, this positive charge on electronegative element makes it unstable. For that, this bond breaks and these two electrons are supplied to OH2 and it becomes H2O molecule and gets detached. At the same time, because these two electrons are transferred to oxygen, at the same time, this gains positive charge, and that's why the negative part attacks on this electrophile. So this one is acting as electrophile, this one is acting as nucleophile, alcohol actually acting as electrophile. Again, there's a substitution reaction. OH is replaced by bromine. It was OH attached to RCH2. Now it is bromine attached to RCH2. You need to write and memorize these two mechanisms. In both cases, first it is addition. Okay? In this case, whole alcohol gets attached to the positive carbon through O, through oxygen. And in next step, hydrogen gets detached. That's why this is OH bond cleavage. Next is alcohols as electrophile. In this case, again, first is addition, but addition of protonation. And then the nucleophile and electrophile, which is actually alcohol converted to electrophile, they combine, H2O is detached. Now examples, examples of first time where OH bond is broken. So there are these examples: reaction with metals, reaction with aqueous sodium hydroxide, reaction esterification, and then the last one, acetylation. Reaction with metals, reaction with aqueous sodium hydroxide, reaction with metals means sodium, aluminium, etc. Reaction with sodium hydroxide aqueous means aqueous NaOH. Although in case of NaOH and Na, both the products will be same. Esterification means ester will be formed. Acetylation means acetyl group will get attached. Acylation, acyl group will get attached. So the first one, reaction with metals. Alcohols and phenols both. With metals, both react. Alcohols and phenols. Why I am saying so? Because in next one, it will be only phenol. In case of metals, alcohols and phenol both react, such as sodium, potassium, aluminium, etc., to yield corresponding alkoxide, phenoxide, and hydrogen. This is the common reaction. You have alcohol or phenol here. Sodium alkoxide or phenoxide will be formed depending upon whether you have used aliphatic alcohol or aromatic phenol. Hydrogen will be evolved. Reaction with aluminium, for example, will be like this. Again, aluminium alkoxide will be formed, but we will call it, in this case, aluminium tert butoxide because we have three alkoxide. That's why tert butoxide from tert butyl alcohol. Next example, simple phenol, sodium phenoxide. Same reaction will be with potassium also. So in place of sodium, you can have potassium phenoxide. Second one is reaction with aqueous sodium hydroxide, only phenols. With metals, sodium, potassium, aluminium, both aliphatic alcohols and phenols, both. Okay? But reaction with aqueous sodium hydroxide, only phenols. React with aqueous sodium hydroxide to form sodium phenoxide. So remember the product is same, sodium phenoxide. If you remember in previous case, we used sodium and we got sodium phenoxide. The only difference was there hydrogen was evolved. Same product, hydrogen was evolved. Here, same product, H2O is evolved. That is the only difference. This reaction shows that alcohols and phenols are Bronsted acids. They can donate a proton to a stronger base. NaOH is very strong base. And this H is given as H plus. And that is the definition of Bronsted base. Sorry, Bronsted acid. For example, H2SO4 gives H plus, HCl gives H plus. So that's why it is a Bronsted acid also. Ankur, is there any question? Okay, I have muted your mic. Next is esterification, means formation of esters, very important conversion. Aryl or alkyl alcohols, when reacted with acids, carboxylic acids, they give esters. In place of acid, you can use acid anhydride also. Then also you will get ester. Many cases you will use this reaction to form ester. This one is preferred, the first one, because in this case, water is formed. In other cases, normally you will get something which is difficult to separate. But anyway, that can be separated. So if you are using the anhydride, then also you will get ester. If you are using acid chloride means this is acyl group. This is the acyl group. Then again you will get esters. All three reactions are very important. Conversion of alcohol to ester can be done by carboxylic acid, acid anhydride, or acyl chloride. Acyl chloride is also called acid chloride. In all cases, whether it is aromatic or aliphatic, you will get esters. Last one, remember we are talking about OH bond cleavage. In all these cases, OH bond is getting cleaved. Okay? Here, hydrogen goes away, nitrogen gets attached. OH bond broken. Okay? Here also, OH bond broken. Sodium attached. Okay? In place of hydrogen. Here also, in all cases, this bond broken and this group attached. These two, OH and H, O and OH, they form, sorry, OH and H, they form H2. So these two form ester, these two form H2. Everywhere in this case, OH bond is cleaved. In this case also, acetylation. Acetylation is again introduction of acyl group. This is acetyl group or acyl group. In alcohols or phenols is known as acetylation. This is acyl group or acetyl group. CH3CO, CH3, CH2CO means RCO is acetyl or acyl group. So this is very important reaction where acetylation of salicylic acid gives you aspirin. Aspirin is the medicine which is in disprin medicine, for example, used as blood thinner. To understand, if you don't know already, this whole is acid anhydride. Or simply you can call anhydride if we are talking about the organic chemistry, but it is good to say acid anhydride. This group, only this part, RCO, is acid or acetyl. And RCOOR is ester, which is written as ROCOR, both same. Now, if I talk about the IUPAC name, as I said, acetic anhydride is common name, but if you say the IUPAC name, in this particular case, it is ethanoic hydride, this one. Acid anhydride, acetic anhydride, why I'm saying? Because there are two carbons. Otherwise, acid anhydride, common acid anhydride, common acyl. So I'm just mentioning it again so that there is no confusion. When I am saying acyl, this is generic, means it is RCO. It is acyl. But if I am saying it acetyl, means I am saying it because there are two carbons. So it is specific depending on number of carbon atoms. When I am saying acid anhydride, this is generic. Okay, means it is RCO whole twice O. This is acid anhydride. But if I'm saying acetic anhydride or acetyl anhydride, it is specific that I am talking about CH3CO. Acetic anhydride, why? Because there are two carbons. But systematic IUPAC name is ethanoic anhydride. Whether you write this one, you are not going to lose marks, remember. Acetic anhydride is correct, ethanoic anhydride is correct. Now reactions, examples where CO bond is broken. Reaction with hydrogen halides, reaction with phosphorus trihalides, and dehydration. So here we have three. And this one is specifically important from mechanism perspective. Mechanism is asked quite a few times. Dehydration of alcohols, mechanism is very important. First one, reaction with hydrogen halides. Hydrogen halide means HCl, HBr, etc. And this one is very common. X will get attached and this will form H2. Alcohols react with hydrogen halides to form alkyl halides. And this is the preparation methods we have talked about in the previous chapter, the 10th chapter, preparation of haloalkanes. This was the reaction, if you remember, for the preparation of haloalkanes that are OH reacted with HCl and you got RCl. Who will tell me the name of this combination, HCl and ZnCl2? Yes, Shashwat. Good. Mehak, Ashi, good. So it is Arohi, Vanna, good. Devve, good. So it is Lucas reagent, which we talked about in previous chapter also. And this is the Lucas test basically for primary, secondary, and tertiary alcohols. Very important test. So alcohols are soluble in Lucas reagent, that is concentrated HCl and zinc chloride, while their halides are immiscible and produce turbidity in solution. So in case of tertiary alcohols, turbidity is produced immediately as they form the halides very easily. So this we use to distinguish primary, secondary, and tertiary alcohols. The preparation method basically. So primary alcohols do not produce turbidity at room temperature. It means if it is primary alcohol, we will not get turbidity. Turbidity means the white colored color within the solution. Turbidity, you can understand something in transparent, say water, and if you drop milk into it, so the milk white color will disperse in the transparent water in the form of cloud. Okay, something like cloud. That is called turbidity. So that type of turbidity will appear with tertiary alcohols when reacted with Lucas reagent. Primary alcohols do not produce turbidity. And secondary alcohol give turbidity when we shake and in 5 minutes. 2 degree alcohols give turbidity in around 5 minutes, not immediately. So in tertiary alcohols, that's why it is written immediately. The moment reaction is carried out, you get turbidity. Tertiary. Next reaction with phosphorus trihalides. And this is again one of the preparation method of haloalkanes from alcohols. Okay? It was there in preparation method of haloalkanes. Alcohols, when react with trihalides of phosphorus, we will get haloalkanes. It is specifically for chlorine and bromine only. So trichloride and tribromide only. Third one is dehydration, where CO bond is broken. So if you see in all these, CO bond is getting broken. Here, say this is CH3OH, CO bond gets broken. Here also, CO bond gets broken. Whole OH goes away. Dehydration, again, same thing. CO bond gets broken. So alcohols undergo dehydration, that is removal of molecule of water to form alkenes. So in this case, along with OH, hydrogen from the adjacent carbon also goes away. That's why we say that it is dehydration. OH goes away. So for example, if it is CH3, CH2, CH2, OH, this OH will go away and one hydrogen from here will go away. So if I write it like CH2, this whole will go away. No, sorry, this is again on this carbon, not this is the adjacent carbon. So this whole goes away. So when this OH and H, these two go away, double bond is formed here. This becomes double bond. Mechanism is important here. Now, these form alkene on treating with protic acids. Protic acids means which release hydrogen. There are acids, for example, when we say BCl3, this is acid because it is looking for electrons. Okay, but it is not protic acid because it is not releasing hydrogen. H2SO4, H3PO4 are protic acid. BCl3 is Lewis acid, electron acceptor. So this is how it happens. OH from one carbon, hydrogen from the adjacent carbon. These two go away in presence of protic acid and form alkene. So for example, ethanol undergoes dehydration like this. CH3, I write it like CH3, CH2, OH. This OH, say I write OH here and this OH and this H. These will go away and double bond will appear here. Dehydration. Secondary and tertiary alcohols are dehydrated under milder conditions. So if you see here, the temperature is 443 K with H2SO4. It is primary alcohol. But for secondary, it will be less 440 and 354. And here you don't need H2SO4. Even H3PO4 will do. 85% here, even 20% H3PO4. In this case, H2SO4 is required. Here, milder conditions. you will get alkenes. Mechanism is same. OH goes from one carbon, CO bond is broken, and hydrogen goes from adjacent carbon. And formation of alkene is as per Setzer rule. And I hope you remember the Setzer rule. So thus the relative ease of dehydration of alcohols is tertiary easiest, secondary not that easy, primary toughest. Okay. So mildest conditions required for tertiary. Temperature 358 K and only 20% S3P. Tertiary carbocations are more stable and therefore are easier to form than secondary and primary carbocations. Hence, tertiary alcohols are easiest to dehydrate. So if the reason is asked, this bond is being broken and this bond is being broken means it can form tertiary alcohol. The tertiary carbocation more stable when formed. That's why easier. Okay. Now the mechanism, as I said, mechanism is very important in this case. First step is formation of protonated alcohol. And you remember the broad mechanism I told you that first protonation hydrogen gets attached. After that bromine attacks. So that is similar, but you need to write in 3 steps. Formation of protonated alcohol is that the lone pair of oxygen attacks on the proton released by alcohol. That's why it has to be conducted in the alcohols, in presence of alcohols which provide proton. So those acids which provide proton are used here. So this is addition intermediate is formed, which is called protonated alcohol. And oxonium ion. So remember the names here. Oxonium ions will be formed when oxygen of not only alcohol, oxygen, if oxygen of any molecule which has lone pairs attacks the proton and forms this type of product. It is called oxonium ion. And the reason is very simple why it is called oxonium ion, because the charge is on oxygen. This molecule now has charge, that's why ion. Oxygen has charge, that's why oxonium ion. But this is unstable because oxygen cannot have positive charge. Electronegative cannot have positive charge. So next step is formation of carbocation. Carbocation more stable, for example, tertiary, that will be easiest. But in this step, if you have old version of NCRT, there this reaction is given, which is not correct. So this is just a misprint there. But in new NCRT, this has been resolved. So this is the slowest step basically, formation of carbocation, and hence rate determining step. It determines the rate. So it is similar to, for example, you have flow of water through a pipe. So this portion, first step is wider. So water is flowing from here. Here also it is wider. Water can flow easily here. But suppose in between, this is narrow. So where it is narrow, in case of reaction, it is slow. Okay? So in case of reaction, I will say here it is fast, here it is fast, here it is slow. This will decide the rate of flow of water because it will not allow maximum amount of water. Similarly here, slow step decides the rate of the reaction. And this is the reaction. So what happens? This is unstable, so this bond breaks. And this bond breaks, carbon gets positive charge, and this water molecule gets detached. So formation of carbocation, second step. First step is protonation. Oxygen attacks on proton received from acid. Second step, formation of carbocation. Unstable ion, oxonium ion. That's why carbocation formed, water released. And water released, that's why this is called dehydration reaction. Okay. Then formation of ethene by elimination of proton. Now this is positive, add carbon to release this positive charge. This hydrogen gets detached and these two electrons form the double bond. Now this is stable. This proton we get back. So first we got this proton from acid, and after reaction is completed, it is used and provided back to us. This step is also known as deprotonation. Formation of ethene by elimination of proton is actually deprotonation. Proton is removed. The steps are protonation, formation of carbocation, deprotonation. Simple. The third step is this carbocation itself. Okay. Carbocation or carbanion do not have free existence, cannot exist standalone. They cannot exist. Okay. So they need to be converted to some stable molecule. For that, what happens? This positive charge is neutralized by the electrons which move from here to here. So two electrons are moved here, these two. And because now hydrogen doesn't have any electron with it, so it is detached as H plus. Because normally hydrogen has one electron, but if it does not have any electron, it is H plus. So this H plus we got back. And these two electrons form double bond here, in which one electron is of this carbon. This carbon had one electron in this bond, so that comes here. And the other electron is provided to this carbon. Okay. That's why double bond here. The acid used in step 1 is released in step 3. So this is released in step 3. To drive the equilibrium to right, ethene is removed as it is formed. This ethene is removed quickly from the reaction mixture. As per Le Chatelier's principle, reaction goes forward. Now, reactions of alcohols and phenols involving cleavage of OH and CH bonds. Oxidation, very important one. Oxidation of alcohols involves the formation of a carbon oxygen double bond with cleavage of an OH and CH bonds. This is how it looks like. Here you have CH bond, and here you have OH bond. So OH bond gets cleaved and CH bond gets cleaved. And you get a carbonyl group. In oxidation. And you remember we talked about that alcohols on oxidation will give you either aldehyde or ketone, depending on whether you have primary alcohol or secondary alcohol. So that's what is happening here. We have alcohol and we are getting this carbonyl group. It can be aldehyde, it can be ketone. Aldehyde on further oxidation will give you acids, carboxylic acids. Okay. So these are also known as dehydrogenation reactions, as these involve loss of dihydrogen, okay, from an alcohol molecule. Dehydrogenation, hydrogen and hydrogen go away. So these two hydrogen go away. So that's why dehydrogenation. With mild oxidizing agents, a primary alcohol is oxidized to an aldehyde, which in turn is oxidized to carboxylic acid. This is something what I explained in on previous slide also. So alcohols on oxidation, we will get aldehyde, and aldehyde will give us carboxylic acid. One day with mild oxidizing agent. Okay. Strong oxidizing agents such as acidified potassium permanganate are used to for getting carboxylic acid from alcohols directly. We will be using all these in conversions. Remember all these agents, reagents, which we will be using. So in this case, for example, here I will tell you CrO3. In this case, acidified potassium permanganate. So if you use acidified KMnO4, the alcohol will directly get converted to carboxylic acid without getting converted to aldehyde. Now, CrO3 in anhydrous medium is used as oxidizing agent for isolation of aldehydes. For aldehydes, we will use CrO. A better reagent for oxidation of primary alcohols to aldehydes in good yield is PCC. Normally, PCC will be given, but you need to know the complete name. Pyridinium chlorochromate. Pyridinium chlorochromate. Write it down. We will be using it extensively in conversions. Remember, oxidation of primary alcohols to aldehydes. Wherever required, use this one. If you have to convert primary alcohol to aldehyde, invariably use PCC, nothing else. Although there are, other possibilities. We can use CrO3. PCC, that is pyridinium chlorochromate, is a complex of, that is mixture of, and then obviously complex compound, chromium trioxide and pyridine and HCl. So we are using again CrO3, but CrO3, then pyridine and HCl, when they mix, they form a complex which is known as PCC. So if it is primary alcohol, you use PCC, you get aldehyde. Remember, PCC does not have any effect of a double bond if present in the chain. Write it down somewhere. Very common question appears from here. PCC does not affect the double bond present in the carbon chain, it will only oxidize alcoholic group to aldehydic group. Double bond will remain intact. Secondary alcohols are oxidized to ketones by chromic anhydride. So it is known as chromic trioxide or chromic anhydride. Both names are used. Also known as chromic oxide. Okay? Also known as chromic oxide. So remember this reagent. Secondary alcohols are oxidized to ketone by CrO3. Basically, it is same thing. Alcohols to aldehydes or ketones, you can use CrO3. If it is primary alcohol, you will get aldehyde. If it is secondary alcohol, you will get ketone. But if you use acidified potassium chromate, then you will directly get acid. You will not get aldehyde. Tertiary alcohols do not undergo oxidation reactions. Question appears from here also. Okay. Under strong reaction conditions such as strong oxidizing agents KMnO4 and elevated temperature, high temperature, cleavage of CC bonds takes place and a mixture of carboxylic acids containing lesser number of carbon atoms is formed. But oxidation does not occur. Tertiary alcohols are not oxidized. Okay. But a mixture is obtained even if you use KMnO4, which is very strong oxidizing agent. KMnO4 is a strong oxidizing agent. That's why this converts alcohols, primary alcohols, directly to acid. But if it is used with tertiary alcohols, it gives you mixture of carboxylic acids containing lesser number of carbon atoms. Now this one is very important. When the vapors of primary or a secondary alcohol are passed over heated copper at 573 Kelvin. This temperature is very important and will be used many times. 573 K. Dehydrogenation takes place and an aldehyde or a ketone is formed while tertiary alcohols undergo dehydration and alkenes are formed. So remember what I am talking about. When vapors of primary and secondary alcohols are passed over heated copper at 573 K, water molecule is removed and you will get aldehyde and ketone. While tertiary alcohols will give you alkenes, dehydration. So dehydrogenation and dehydration, these are two processes. So because here in this case, primary and secondary dehydrogenation happens. That's why you get aldehyde and ketone. And remember what I said that if it is HCOH and we are talking about both bonds got broken. So you got C double bond O and H2. I'm talking about this part, dehydrogenation. So this is either aldehyde or ketone and hydrogen removed, dehydrogenation. So this happens with copper also, heated copper. You have to use the vapors of primary and secondary alcohols at 573. With same conditions, if it is tertiary alcohol, then dehydration will take place. Water molecule will go away and alkene will be formed. Reactions are like this. If it is primary alcohol, condition 573K, and another condition that this is actually in vapor form, you get aldehyde. If it is secondary alcohol, vapors, same condition, copper 573K, you get ketone. But if it is tertiary, vapors, same condition, you get alkene. Because behavior is different, that's why this reaction is very important. Biological oxidation of methanol and ethanol in the body produces the corresponding aldehyde followed by the acid. From here also question appears. You might have heard that sometimes uh, due to poisonous liquor, quite a few people die. And what is the compound which is responsible for their death? We will be talking about. Okay. So normally, what is served as liquor is ethanol. But when liquor is made, at homes or some small scale industries illegally, then some amount of methanol is also produced. So sometimes by mistake, people drink ethanol mixed with methanol, also called denatured alcohol. So this is responsible for death. Why? There is reason. In the body, methanol is oxidized first to methanol and then to methanoic acid, which may cause blindness and death. So it is actually conversion of this methanol first to methanol. So this is CH3OH first gets oxidized to methanol and then it gets oxidized to methanoic acid. This is responsible for blindness and death. So a methanol poison patient is treated by giving intravenous infusion of dilute ethanol. So how treatment is done and why ethanol is given? So when methanol is there, CH3OH, this reaction is happening. This reaction is taking place. We need to make the rate of this reaction slow. We cannot avoid this reaction at all, right? So normally it is not possible to stop this reaction in the body. So what is done? Ethanol is introduced in the blood. This ethanol is introduced. What happens? The enzyme responsible for oxidation of aldehyde to acid is swarmed allowing time. So what happens? This happens CH3C sorry CH3OH conversion to HCHO is done by some enzyme. So what happens when we introduce C2H5OH? This also gets converted to aldehyde by the same enzyme. Now the availability of enzyme for the first reaction becomes half or even less if we can give more ethanol. So ethanol is introduced so that ethanol starts using the same enzyme which is converting methanol to methanol. Acid is swarmed means Here, that enzyme is used there, rather completely used for methanol conversion to methane. I think we finished quite early. Any question till here, or anything you want to discuss, anything not clear in this chapter, you can let me know. Just unmute your mic and let me know anything. Specifically, I am asking Anish, Ankur, Arohi, Shivangi, Sneha, Sudipta, Sohani, Sohina. Any problem you are facing, you need to let me know. Okay. Ashi, I am planning a session for to discuss the assignments, all questions of the assignments which you are not able to do. Yes, doubt session. The next session will be doubt session. Okay. So that's what I was going to tell you also, that I have received very few questions which you have faced problems. Okay. Shivangi, okay, I'll explain the second step of dehydration. Doubt session, Yastika, yes, we will be doing there. Okay, so that's fine. You can leave now. So take care. Good night. Bye bye. Shivangi and others can stay if they want more clarification about the second step of dehydration. Otherwise, that's fine. Take care. Good night. Bye bye. Okay. So this is the mechanism of dehydration. The second step is this one. Second step is, once protonation has taken place, this oxonium ion has been formed in first step. Now, second step is here dehydration basically. Formation of carbocation is dehydration. This charge, positive charge, cannot remain on oxygen because oxygen is electronegative. So positive charge on an electronegative element makes that species unstable. So it is true for negative charge on electropositive element also. So for example, there is negative charge on carbon, that will also be unstable. So because it is unstable and positive charge logically should be on carbon, so that's what happens. The positive charge gets transferred to carbon and we get a carbocation. How it happens? It happens because this oxygen has positive charge. It means it is deficient in electrons. It has less number of electrons as compared to what it should have. So that's why this bond gets broken. And both the electrons are provided to this oxygen. And this oxygen, as usual, now have two lone pairs. One was already there and one got transferred. So this is H2O now. But because this carbon now does not have any electrons of this bond, so that's why it gains positive charge, because it has lost its own electron as well. Here, one electron was of oxygen and another electron was of carbon. But both these electrons move to oxygen. That's why this carbon gained positive charge.